Okay, so we're going to do 5.3 part 3. There's 4 parts to 5.3 because it's all about graphing. So far we've learned about increasing, decreasing, concavity. Now we're going to talk about horizontal asymptotes. All right, and this isn't typically something that's taught at the beginning of calculus. Usually people will talk about it for BC, or they'll talk about it at the end of calculus. But I've always decided to teach it in my AB course because a lot of times there's limit questions on the multiple choice that are very easy to find with Lhopitals rule. So we're going to learn Lhopitals rule. Nick Chula refers to this as the hippo. I'm not really sure why. There's not really an H-I-P-O in there. But if you hear him refer to that, that's what this is. So Lhopital. All right, Lhopital is a name of a mathematician. Okay, so it says, remember when we computed limits, we sometimes plugged in the values and we got like 0 over 0 or infinity over infinity. And then we did all these different tricks. We did like factoring tricks, conjugate tricks. We did like tables of values. So lots of different things, and we could then compute the value of the limit. So for example, if we had the limit as x goes to 1 of x squared minus 1 all over x minus 1, if we plug in 1 originally, we get 0 over 0. So for this one, it's very easy to do a factor trick. You can just factor the top, factor the bottom, cross out the x minus 1s, and you can see the limit right away. But this is not always the case. So an indeterminate form of a limit is when a limit results in a number that cannot be determined, like the following. So you might have like 0 over 0, infinity over infinity, 0 to the 0, infinity minus infinity, which most people are like, oh, well, that's 0. But what if you had a really big infinity, like x cubed minus x? You know what I'm saying? And then the limit as x goes to infinity. So there are different things. And there's a lot of other ones, but those are the main examples we're going to deal with. All right, so suppose that f and g are differentiable on the interval a to b, except possibly at some fixed point c in the interval. So at some point c, maybe it's undefined. Maybe there's an open circle. So suppose that the limit as x goes to this value of f of x over g of x has the indeterminate form of 0 over 0 or infinity over infinity. So those are the only two cases that you can have for Lhopital's rule. So infinity over infinity or 0 over 0. And let's suppose that the limit as x goes to c of f prime of x over g prime of x equals some number. So it exists. So it's not 0 over 0 or infinity over infinity. Then the limit as x goes to c of f of x over g of x equals the limit as x goes to c of f prime of x over g prime of x, which we said was that L value. Okay, this statement is also true for right-hand limits and left-hand limits. So basically, you can just take the derivative of the top and the derivative of the bottom. So that's kind of counterintuitive, because when you guys have something like 2x over, I don't know, x plus 2 squared, when you think of taking the derivative of that, what do you think of? Quotient rule, right? You know you have to use quotient rule. So I'm telling you, you can just take the derivative of the top and the derivative of the bottom for this Lhopital rule, which is kind of weird because you're like, oh, it's a quotient. I have to use my quotient rule. So we'll talk about it. Okay, so for example, so let's say I have the limit as x goes to 0 of cosine, or 1 minus cosine of x all over sine of x. So first we need to check, is it 0 over 0 or infinity over infinity before you can use Lhopital's rule. So let's think about it. Here's a radian measure of 0. So cosine of 0 is 1. Sine of 0 is 0, right? Cosine is the x value, sine is the y value. So if you're checking, you would have 1 minus 1 over 0, which is 0 over 0. So when you get that, you can use Lhopital. So I usually do a limit as x goes to 0 of 1 minus cosine of x all over sine of x. And then I want to somehow write that I've used Lhopital. So I put like an h over the equal sign. Okay, so what's the derivative of the numerator? Sine of x, right? So I get the limit as x goes to 0 of sine of x over what's the derivative of the denominator? Cosine of x. So now can you plug in the number? Can you plug in 0? Yeah, sine of 0 is 0. Cosine of 0 is 1. You get 0 over 1, which is 0. Okay, next one. Why are we using this? Okay, because we're going to often talk about the limit as x goes to infinity. So think about a graph. What does that mean when you talk about the limit as x goes to infinity? Alex, you with me?
Yeah.
Okay, what's it mean for the limit as x goes to infinity for your graph? It's talking about the end behavior. Do you guys remember end behavior from Algebra 2? It's talking about what happens on the end of your graph. So as x goes to infinity, it's talking about right here. So if we have horizontal asymptotes, like if as x goes to infinity, if the y value is always going towards 1, that's going to be important to us. We want to know what's happening on the ends. Okay, so in order to compute some of these, sometimes it's useful just to have Lhopitals rule, so you can quickly do it. Okay, so this next one, so I have the limit as x goes to 2, so we're going to check. If I plug in 2, I get 0 over, plug in 2 on the bottom, so 4 minus 6 plus 4. Oh, yeah. So this one you can actually plug in, can't you? 4 minus 6 plus 4. So this one is just 0. Must have messed that one up. I think I wanted that to be 0 over 0. All right, so the next one, so limit as x goes to 0. Can you plug in this one? 0 over 0. So we're going to use Lhopitals rule. So I have the limit as x goes to 0. Derivative of sine, cosine. Derivative of x, 1. So as x goes to 0, you get cosine of 0 is 1 over 1. So your answer is 1. Okay, the next one. So if I plug in 0, so what's the tangent of 0? So it's sine over cosine. Tangent of 0? 0. So you get 0 minus 0 over 0. So the limit as x goes to 0, because that was 0 over 0, of derivative of tangent, secant squared, x, minus derivative of x is 1, all over 3x squared. Okay, let's think about this one. It's what? Still 0. So if it's still 0 over 0, what can we do?
Again.
Do it again. Now it's a little bit harder though, because now you have secant squared. So think of secant squared as secant x squared. So you're going to have 2 secant x times derivative of secant x, secant tangent x, minus 0, all over 6x. Okay, think about secant x and tangent x. So secant of x is as x goes to 0. It's 1 over cosine. Cosine is 1, so 1 over 1. What's tangent? So this is 1, this is 1. So tangent is sine over cosine. So it's 0. So I get 0 over 0. Do it again. This one is long, yeah. Okay, so if you plug it in, now you have, so let's think of it as limit as x goes to 0 of, so reduce down the 2 and the 6 and make it 3. So you have secant squared x tangent x all over 3x. Can you guys tell that this is going to be our last time that we do this? Why? You won't have an x on the bottom, right? It will just be 3 on the bottom. But this one is a little bit hard to compute, so we have to use the product rule. So I have first times the derivative of the second, so derivative of tangent is secant squared, plus derivative of the first, so we already did that, so we said it's 2 secant x times another secant tangent, so secant squared x, tangent x, times tangent. But you could have kind of shortcutted that because you knew it was going to be multiplied by tangent, which we know is 0. So all of that's gone. That's all 0. So now you have secant squared times secant squared, and when we plug in x, we get 1, right? Secant of 0 is 1. So your answer is 1/3. Okay, this one, the limit, you're just approaching from the left, which is fine. So left and right-hand limits work the same way. So when you plug in pi, so think about your unit circle. Pi's over here. That's the point, -1, 0. So sine is 0, cosine is -1. So what about this one? It's what? 0 over 2. Is that allowed? Yeah, that's 0. So that one exists. Okay, so it says, notice Lhopitals rule does not cover all indeterminate forms. So you also have these other ones, like you could have infinity minus infinity, 0 to the 0, 1 to the infinity, oh, I forgot to say that one, and 0 times infinity and infinity to the 0. Okay, these are all different indeterminate forms. Okay, the goal is to try to get one of these into the form 0 over 0 or infinity over infinity, so you can use Lhopitals rule. So when you see an example like the first one, so I have the limit as x goes to infinity of 1 over x squared minus 1 over x to the 4th. So this is talking about what's happening on the end of the graph. So you have some kind of graph you're talking about as x goes to infinity. Okay, so this is why it's going to be useful for horizontal asymptotes. Okay, if you plug in infinity, do you guys see that you have like 1 over infinity minus 1 over infinity? Okay, so that's not really in that indeterminate form. It's not like 0 over 0 or infinity over infinity. So we're going to try to get it in that form. Okay. So what do you guys think we're going to do? Kind of. I heard someone say it. Common denominator. Well, yeah, let's get common denominators. I like what you're thinking, but if you get them with the negative powers, then you're just going to have like infinity to a negative power, and that's still kind of weird. Okay, so common denominator. So the limit as x goes to infinity. So I'm going to multiply the first one by x squared over x squared. So I get x squared over x to the 4th minus 1 over x to the 4th. So it's x squared minus 1 over x to the 4th. Okay, so now is it in that form? Do you guys see how it's infinity over infinity? So that means we can use Lhopitals rule. So when I do that, I get the limit as x goes to infinity of 2x over 4x cubed, which that reduces down, so you don't really have to use L'Hopital again right yet. So I have 2 over 4, so that makes 2. So I have 1/2, and then I have x squared on the bottom. So now if you plug in infinity, what do you get? So it's not plugging in infinity, but you know what I'm saying. So take the limit as x goes to infinity. You have 1 over a really, really huge, huge, huge number. So it equals 0. All right, so number 4. So I have the limit as x goes to infinity of the square root of x squared plus 1 minus x. Okay, so it says note, if you plug infinity in, so when I say that, I'm not really plugging infinity in. I'm taking the limit as x goes to infinity. You get infinity minus infinity, which you cannot determine. It's indeterminate. Let's try to write the function as a fraction. So whenever we have square roots, we always think of conjugates. So we're going to multiply by the conjugate on the top and the bottom. So I'm going to multiply by the square root of x squared plus 1 plus x all over the square root of x squared plus 1 plus x. So when I do that on the top, I'm going to get x squared plus 1 minus x squared. So you're foiling it out. The outer and inner terms cancel. On the bottom, you have the square root of x squared plus 1 plus x. So I get 1 over the square root of x squared plus 1 plus x. So can you guys tell what this is going to? Yep, it goes to 0 as well. Oops, I don't know why I wrote there. Equals 0. All right. Okay, so what does this mean about the graph? There's a horizontal asymptote at 0. So let's see what that graph looks like. So let's go to Grapher. Okay. So see how it looks like this? So as it goes towards 0, you get closer and closer to the axis. Okay, notice if you had plugged in negative infinity, so if you had taken the limit as x goes to negative infinity, do you see how that doesn't have the same horizontal asymptote? So you don't always have the same number that you're approaching for positive and negative infinity. So if you're really trying to find the horizontal asymptote, you need to find it for both things. You need to take the limit as x goes to infinity and take the limit as x goes to negative infinity as well. So I just wanted to show you that. So on the right side, there is a horizontal asymptote of 0. Okay, so the last one, it says sketch a graph of y equals x squared, x minus 2 to the 4th times x plus 1 to the 3rd times x minus 1 by finding its intercepts and limits as x goes to infinity and as x goes to negative infinity. So we're finding the horizontal asymptote on both sides. Okay, so if I find the x-intercepts, you plug in 0 for the y. So you have 0 equals x minus 2 to the 4th times x plus 1 to the 3rd times x minus 1. So we'd get x equals 2, x equals negative 1, and x equals 1. Do you guys remember what multiplicity means? No? No one remembers multiplicity at all? You have the same root multiple times. So what does that mean about the graph? So for this x equals 2, this is a root 4 times. So it has multiplicity 4. Negative 1 has multiplicity 3. And 1 has just multiplicity 1. So if I zoom in on that particular root, the multiplicity tells you what kind of shape it is at that root. So if it has multiplicity 4, that means at 2, you're going to look like a quartic function, so degree 4. If you have multiplicity 3, you're going to look like a cubic function at negative 1. Okay, so that's going to kind of help us out a little bit too. Okay, so we have at 2, we have multiplicity 4. At negative 1, we have multiplicity 3. And at 1, we have multiplicity 1. So at 1, it just goes straight through. And now these can go either direction. It could look like that, or it could look like that. So we have to kind of determine that as well. So it's one of those things. Okay, y-intercept, how do I find that? Yeah, all the x's are 0. So you'd get y equals negative 2 to the 4th, so 16, times 1 cubed, so 1, times negative 1. So I get negative 16. So it's way down here. Okay, so limit as x goes to infinity. you guys tell what it is? It's not hard. We're not using Lhopitals rule. It's infinity. You just plug infinity in. Okay, now the limit as x goes to negative infinity, though, is a little bit harder because you really need to think about the sign. So on these, it was like a big, huge number to the fourth, a big, huge number to the third, a big, huge number. So when you multiply all those big, huge numbers that are all positive by each other, it's positive. But think about the negative big, huge number. So this first one would be positive. If I had a negative huge number right here, it's going to be cubed, so it's negative. And then a negative huge number minus 1 is still negative. So positive times negative, that's also positive infinity. So on the ends, we look like this. So now we connect our points. So we're going to come down. I kind of don't like that one. We'll go more up here. So I come down. I'm going to hit this first one like, well, it's at -1, so like a cubic function. So it's going to look like that. So you're going to come down, and you're going to do a little cubic function squiggle. Ugh, I keep crossing the axis. You can't cross the axis, can you? Because you got to cross all the way down here. So then you go down, and it might go past that point, but that's where it's crossing the axis. And then it comes back up, and it goes through 1 like a straight line. And then it comes down, and it's going to go through 2 with multiplicity 4. So it's going to look like something like that. So it's going to come down, and it's going to flatten out a little bit, and then pop back up. So that's kind of what that graph will look like. Crazy.